GameSci.com. GameSci.com.
Howdy, partners! I'm Professor Chris Ferguson, and let's giddy on up and learn about database and records. Let's create a database to track online game user accounts. A database is a collection of records. If 500 players have signed up for your online game, there'll be 500 records in the database. Now, only 3 records are shown in this example, but the ... dots down here imply there could be many, many more records. Size does matter. Hundreds of records, you could probably get away with a simple disk file. But if you have millions of records, you really want to use a database. A record is a collection of fields: email, play ID, screen name, level, money. A set of information that describes something, in this case an online game player. Records in a school database would describe a student. Records in a car dealer's database would describe a car. Only 5 fields are shown in this record, but see the ... dots here at the end? That implies there could be more fields. For disk files, the number of bytes in each record is important. Instead of using a database, if you're going to write this data to your own disk file, you want to know exactly how many bytes of data each record occupies. A field is a piece of record. It could be a string, an int, or a float. This is the email field right here. For a database, one of the fields needs to be a key field, something that uniquely identifies the record. Email, or field 0, is a good identifier key for 2 reasons. First, it's unique, and second, people remember it. It could be used as their logon name. A field is a piece of record. It could be a string, an int, a float. It looks like play ID or player ID is an integer number. It's a column in the database, a column in the table. Play ID or field 1 is a player ID number that uniquely identifies the user. This number may be needed for billing or accounting purposes, but it makes a terrible logon name because nobody remembers their player ID number. A field is a piece of record. It could be a string, an int, a float. Here's 3 more fields that I chose to highlight. The rest of these fields, screen name, level, and money, and the ... dot means there could be more of them. In total, they describe 1 player in the game. The numeric field may be stored as numbers or ASCII strings of characters. Most important is how many bytes of data one record occupies. If you are going to be storing this data in your own data file, you want to know exactly how many bytes of data each record occupies. Rows and columns. You've got to get familiar with the table format. Creating a data file on disk is a simple database. If you just wrote all your data out to rows and columns in a plain old text file, technically that is a database. But let's talk about DB terminology first. A relational database stores information in row and column format. When you extract information from the database, what we've been calling a record is what we call a row from the database. And a field is what we call a column in the database. Keep in mind we're learning databases bottom up, how to build a DB from scratch. We looked first at writing this data to a text file, and now we're going to look at storing it in a relational database. Whether you choose to call these rows or records, columns or fields, doesn't really matter. Just about everything in computer science has multiple names. So just get used to it. Some people call these records, some people call them rows. Some people call these fields, some people call these columns. When I think of a table, I think rows and columns. Back to disk files. A critical step in storing data in a database is converting a record into an array of bytes. Some decisions need to be made before you can do this. Are letters going to be 1 byte ASCII or 2 byte Unicode? Are numbers stored in integer or float format or as strings of letters? The easiest solution is to store plain text, then convert the letters, like the string 42.23, to a number after it is in RAM memory. A lot of the simple databases out there just store everything as plain text, and then when you extract it, it converts it to a number. Hard disk drives are block addressable. That means an entire block or sector of data must be read or written at a time. You cannot just read 8 bytes of data from a disk. You read the entire sector, say 512 bytes, then extract the 8 bytes you want. Efficiently storing records into disk sectors can greatly improve the speed in which data can be accessed from a disk drive. If you're going to design your own data files and store them yourself on the hard drive, you have to be very careful on the size of each record, and then you want to size each record to efficiently match the disk sector size that you are using. Step 1 in any database is to determine the fields or columns of the table. Decide on the key fields. Is it going to be an email or a phone number or a social security number? Something that can identify each record. Add additional fields your application will need to process each record. A game player record needs a screen name. A car record needs a license plate. A student record needs a GPA. What is the information that completely describes one entity that you're storing in the database? Sometimes it'll be 4 fields, sometimes it'll be 8 fields. What information do you need to store in order to complete your application? If you will be writing this data to your own data files rather than using a database, you must decide on a format for each record. Are you going to use fixed length for the record? What size fixed length? CSV or comma separated values for each record? Or even a Python dictionary? When I'm writing disk files, I kind of like using Python dictionaries because they're a lot easier to load, read, change, modify. If you use a database program to store your data, it will handle the format for you. You can focus on the type. The screen name is going to be text. Level is an integer. Money is a decimal number. So the time has come for you to write your data to the disk drive. Option 1, you can plan on creating your own data files. That way you will be writing the data to the disk drive. It's time to write the Python code to do that. But there is a second option. What if you use a database manager, a DBM, like SQLite or MySQL, etc.? There are plenty of options when you use a database manager for creating a table on the disk drive. Option number 1 for creating a table on the disk drive is to use a utility program like PHP Admin. These are online utilities that set up the table for you. You tell it what you want, and it creates a file on the disk with the table that you want. Option number 2 in creating a table is you write a structured query language SQL command like create table and have a program create the table out on the disk drive for you. Option number 3, and I'm just starting to use this, is ChatGPT. Just describe the table you want, name your fields, which one's the key, and it will write the SQL for you. Size does matter. How many records? How often are you going to update them? There's no absolute rule on how you should store records to disk. But with a small amount of records, you could use Python to read and write records to a plain old disk file. But when your data size gets large, you have a large number of records, use a DBM like SQLite to read and write the records. What if you're creating a web-based application? Let the DBM MySQL handle the data. A big e-commerce site? Millions of records, maybe you're going to pay the money and use the Oracle database. Let's look at it from a logical view. Let's let the DBM handle the disk read and write for us so we can just focus on the data. Pretty much every website in the world operates in a similar manner. The user makes a request like show me the computers for sale or the videos to watch or the games to download. That request triggers a database query that extracts info from the database. The server then returns the data as formatted HTML or JSON records for display to the user. The client side is the user on the web browser. They make a request over to the server side. A program like Python often queries a database, gets the information out of the database, and then does what? Sometimes they actually create the full HTML and send it back to the user or the client to display. Sometimes server programs actually create JSON objects and send JSON objects back to the client, and then the client format the data for the user. Either way, data is being read from the database and sent back to the user for display. You go onto YouTube and say, show me cat videos. It's going to send back a list of cat videos and display it on the screen. You go onto eBay and say, show me PS5s for sale. It's going to go to the database, read all the PS5s it has, and show them to you. From a logical viewpoint, just think of a relational table as a set of records where each record is divided into fields that describe one entity in the table, like one player/users of an online game. These are all the users that have signed up for the online game. We want their email address. We assign them a player ID. We want their screen name, what level of the game they are, and how much money they have in the bank. Now, this could be virtual money or actual money. But this is the information we have decided we want to store for each player that signs up for our online game. A relational database stores information in row and column format. When you extract information from a database, what we've been calling a record is a row from that database, and what we've been calling a field is a column from that database. So you can see that row 1 contains Tom at Gmail. His screen name is TomTom, and he currently has $12.99 in his bank. Column 2 is all the screen names for the players. Bobster, TomTom, Avenger, J-Man. Get used to this row and column format. That's the logical viewpoint that you should think of data stored in your database. What is a query? It is a question, an inquiry. The foundation of a relational database is the ability to ask the database for data stored in the rows and columns. For example, what are the player IDs stored in the table? If you ask this database table, what are your player IDs? It should return these values right here, or the entire column stored in the database for player ID. The foundation of a relational database is the ability to ask the database for data stored in the rows and columns. For example, let's ask the database what rows have a level equal to 2. The database manager will then go find these 2 rows, see level 2 here, extract that row, and this row, Tom and Tim it looks like, and return those 2 rows to the user. I like to call this table in, table out. Table in is the big table that you're storing in your database. Table out is the sub-rows or the sub-columns that you extract when you ask the database for information. You do not have to access full rows and/or columns. You could ask for specific data. For example, what are the screen name, level, and money where money is greater than 50? If you look at the money column, only 3 entries are greater than 50. And I'm asking for the screen name, the level, and the money only. The phrase I keep using is table in, table out. Table in, or the input table, is the large table, the table where we're storing all our records. Our output table is the subtable we extract with our inquiry. So I took this large table and made an inquiry that just extracted 3 columns. I returned a subtable containing the data returned by the query. And there it is. I asked for screen name, level, and money for everybody that had money greater than 50. This tiny little table over here is the table out. It's the subtable I extracted from the bigger table. Once the subtable is extracted, a simple loop through the data displays the results to the user. This is how every website in the world behaves. It extracts and displays data from the database. So I made an inquiry for screen name, level, and money, where money is greater than 50, and now it's going to loop through and print each reply to my inquiry. There's the second one. For example, go to Amazon and search game controllers. A subtable is extracted from their database, and then a loop displays the controllers for sale, usually in order of highest probability. Many online websites, they want to show you the things they make the most money off first. I looped through again, got to the third entry, and I displayed the third entry. I'm showing the screen name, I'm showing the level, I'm showing their current money amount. Go to YouTube, search on Python programming. A subtable is extracted from the YouTube database, and then a loop displays the Python video on the screen for you. And again, what gets displayed first? The things they make the most money off of. YouTube is ad supported, so they want to show you the views that generate the most money in ad sales. Behind every website is a database. Pages on that site are created by extracting a subtable and looping through it and creating HTML with the data for display. We went into our larger table, extracted a smaller table, and then displayed it on the screen for the user. Pretty much how YouTube works. That's how Amazon works. That's how TikTok works. You go on TikTok, it says show me cat videos. It will extract the cat videos, and trust me, which one are they going to show you? The ones that generate the most ad revenue. Relational database. Let a database do the work reading and writing disk files. Again, you always have a choice. You could choose to write your own data out to the disk files using your own Python coding skills, or you could use an off-the-shelf database manager. Now that we've covered reading and writing files, the next step is to use a relational database program to handle the reading and writing of the files for us. Keep in mind the DBM will store and retrieve the data from the tables and handle the read and write to the files for you. A small database will have one table. A larger database could have 3 tables. Think of a car dealership. They may have a table for the cars for sale. This is a list of all the cars we have on the lot. They'll have a table for their customers. This is a list of everybody that's bought a car from us. And they might have a third table for each employee. So think of a relational database as a set of 1 or more tables. Those tables have that logical view that I've been showing you, row and column format. And the good news is it's the DBM's job to handle the read and write of those tables to files on the hard disk. It greatly simplifies our coding if we let the database manager write the files to disk rather than us writing our own files to disk. To use a relational database, first we create a table. We could use an online tool to do that, or we could write a small program to set up our table. We got to decide on our fields, and once we have that, we can create our table. After that, we want to insert records into this player's table. Data in a relational database is stored in tables. The DBM or database manager handles all the details of storing the data in the files for you, but you do need to understand how tables work. Under covers, the DBM writes the data you place in the table onto a disk file. Each record contains 1 or more fields that identifies the record, like bob@yahoo.com or 12345, and that key may be used to determine where DBM will store the record on the disk. So let's add bob@yahoo.com into our database. Let's do some sort of database query where we pass it our connection and the record we want to store and add a new record to this table. That's a command like insert into players values bob@yahoo.com. This is an example of an SQL command that says I want to insert something new into my table. The DBM decides it belongs in sector 123 and reads sector 123 in RAM memory. It will linear search the sector and find that byte 0 in the sector is free, so it'll insert that record, bob@yahoo.com, into byte 0 of the record. It'll copy the entire record to offset 0 of that sector. Then when it's done, it will write sector 123 back to the disk drive. It'll take 1 disk read, 1 disk write to update the database with 1 row or 1 record in the table. Now the beauty of this is if the database manager is doing this work, you don't have to. You just ask it to insert, it'll figure out where to insert it, and then pluck it in there, read the sector, update the sector, and then write it back out to disk. Let's do a DB query on Tom's record. Add another record to our table. Tom@gmail with a player ID of 76543. Let's put TomTom into the database file on the disk drive. This is an example of an SQL command, or a structured query language command. We're going to insert into players, our table, these values, tom@gmail ... Once again, the DBM decides it belongs in sector 123 and reads that sector into RAM memory. It will linear search the sector and find at byte 128 we have space available for our record. So we'll insert the record Tom at Gmail into that position of the disk sector. It'll copy the entire record to that offset 128. It will then write sector 123 back to the disk drive. Every database update, every database insert is going to require at least one disk read and at least one disk write. Read the disk sector into RAM memory, insert the record, and then write it back out to disk drive. Sue at iCloud with the player ID of 49271 will DB query the Sue record into the database, add it to the table. Again, this is an SQL command, insert into players. Insert a new record into the players table, and the values will be the values you see here in the red box. Insert those values into the database. The DBM decides it belongs in sector 123. So once again, the database manager reads that sector into RAM memory. It linear searches the sector and finds some space available for Sue down there at byte 256. It inserts the entire record for Sue at byte offset 256 of the sector. Copy that entire record at offset 256, then write sector 123 back to the disk drive. Now what you're seeing here, let's say I have a disk sector that can hold 4 records. I've used 3 of the 4 positions in the sector, and I've got 1 free record. Sometimes we call these buckets. If you're just going to use a database, do you have to know exactly how it writes it out to disk sector? Probably not, but you want to know how databases work so you understand how to use them better. Just to be clear, this is the data that is being written into the database files on the hard disk. Once we have populated our table with records, now we can go locate, find, or select data from the disk drive. So let's do a DB find on Sue at iCloud and see what happens. Let's retrieve a record from the players table. Here is what we call an SQL command. Select star from players where email equals Sue at iCloud.com. We're going to ask the database to locate this record. It will find it in sector 123 and load that sector into RAM memory. It'll go to byte offset 0 and look if Sue is at byte offset 0. And that does not match the key Sue at iCloud. So we'll continue to search the sector until it's found or it finds an empty record. We've done 1 disk read here, but there could be multiple records on that sector, so we have to search the entire sector. So we're still searching for Sue. We've done our select. We've loaded 1, 2, 3 in RAM memory. It's time to go to the next record in the sector and see, is that Sue? And once again, Tom does not match. At byte offset 128, we have not found a matching record. So we need to continue the search of the sector until we find it or locate an empty record. We're doing what's called a simple linear search or probe of the disk sector, looking for the record containing Sue. Sector 123 is already in RAM memory. We go down and search byte offset 256, and Sue does match. So what the database manager will do is return the entire record, the entire row, at byte offset 256. This is called a linear search or a probe of the disk sector. And luckily, all of this is handled by the database manager under the covers. Now, if you were to write your own code to read and write the disk, you'd have to do your own search of the records. But thankfully, a DBM automates this for us and does the work for us. What if we tried to find something that wasn't in our table? Let's do a find on xxx at iCloud.com. Let's retrieve a record from the players table, but this time it does not exist. The database manager will determine which disk sector that should be in and load disk sector 123 into RAM memory. Now, it will search the records. It'll look at Bob, it'll look at Tom, it'll look at Sue, and it won't find what it's looking for. It'll finally reach this empty record, and at the point where it reaches that empty record, it decides that xxx at iCloud.com does not exist in our database. It will return a not found empty record, and it indicates that it doesn't exist in our database. What if we searched this whole sector and didn't find it, but it was a full sector? Then it would have to keep searching to the next sector. How do we delete a record from a database? Let's do a db delete tom@gmail.com and delete a record from the players table. The DBM determines that tom@gmail should be in sector 123. Once again, it will read sector 123 into RAM memory. The bucket search finds Tom at byte offset 128. The delete is a find first, then remove. Every delete operation on the database has to go find the record first, and then after it finds the record, then it deletes it. Be careful when you're removing a record. We don't want to mess up the search or the find operation. Remember, the search or the find operation looking for empty records. What we need to do is we have to mark it with a special delete flag. We're going to replace tom@gmail.com with a deleted flag. We don't want to empty the record. That would mess up the search. We're going to write the sector or bucket 123 back out to disk with this deleted flag in the record at byte offset 128. We're going to do one disk read, mark it as deleted, and then one disk write back out to the disk. We want to reuse that space on future insert, but we don't want to count it as empty when we're trying to do a find on it. So if we try to insert a new record into this space, it would use this record. If we were looking for a record, it would go past this record. So we did several operations here. We did an insert, a find, a delete. These all require disk reads and or writes and handled by the DBM, not you. That is a detailed description of how a database works under the covers. The good news is you don't have to be an expert on reading and writing files to use a database. But you do need to understand the logical view of tables in a relational database and learn a few SQL commands that will ask the DBM to do the insert, select, or delete of the records. Students tend to think of databases as complex, complicated, but they're not. If you understand tables and records or rows, or columns and fields, you're well on your way to understanding relational databases. Then you learn a small number of SQL commands, and you can program a database. Database programming is kind of like an iceberg. The complicated stuff is done under the covers by the DBM. We only have to learn that small part of it, understand a table, learn to write SQL commands. SQL databases, Relational Database Management System, RDBMS. SQLite is a free single computer, single user database, which is real easy to use with Python. MySQL is an open source network-based database named after the developer's daughter MySQL can be used for multiple computers with multiple users. SQL stands for Structured Query Language. It's a system-independent language for any RDBMS. The SQL studied here works for most relational databases, open source or commercial, like Oracle. SQLite requires no special setup. It's single user, single computer. MySQL, however, requires a host name, a username, a password, and a database name. The first thing you have to do when you're thinking about using MySQL is find those 4 pieces of information. These are some screenshots from a free web hosting site I was using that supported MySQL. I had to go in and create the database. I named it and said hit create. And then when I looked at my databases, it showed me the database name, it showed me the username, it showed me the host name. I had to go somewhere else to look for the password. See this show hide button? It showed me the password. I just had to go look it up properly. Every host is slightly different, but they're not a whole lot different. Usually on the hosting web page, there's some sort of button to access your MySQL. Just click on it and follow the links. You should be able to find the information you need to set up a database. SQL databases, or Relational Database Management Systems. We'll start with a MySQL example. We're reaching the point in the lessons where it's time to write a Python program to use a database, and I'll start with a MySQL example because it's pretty straightforward. There's two ways we typically use a MySQL database. Number one, online utilities like phpMyAdmin. We saw the screenshot on the previous slide. Most hosts provide a utility to create a database, add tables, and insert and edit data into MySQL. If you go onto your web host and click on the MySQL link, you should have a utility on there that shows you how to set up a database, and even if you want to, use the database. The second way you can use a database is write a Python program to connect and send SQL commands to it to update the database. For one-time tasks, I usually use number one. If I'm just going to set up a quick table and I only need to set up one table one time, I go onto the online utilities to do it. But in this lesson, we'll focus on number two, writing computer programs that use an SQL database. Host equals server.mysql, user equals SQL user, password equals XYZ, and database equals test.db. Start with your MySQL host. Every host is different. When you log on to edit a web page, there'll be a link on or near the control panel with the MySQL settings for your account. The values here are made up. Your host will provide specific values to you. Or you could Google your host name MySQL settings, and it usually has a link to find those set values. What you're looking for on your web host is your host name, username, password, and database name for MySQL. Once you have those four pieces of information, you can write a program to use MySQL. Host equals server.my.sql. Server.mysql, www.gameside.com. There's a reason why the host looks like a web address. It kind of is. Just like a browser connects with a web server to get a web page, an SQL program will connect with the server to access the data in MySQL. Your web hosting company supplies this for you. All you have to do is look it up. User equals SQL user. Security is important when many users are sharing an SQL server. Most hosting sites assign you a MySQL username that may be a variation of your web hosting account username. To be clear, this is a separate logon from your web hosting. When you look up the server address for the host and MySQL, the username should be listed right there next to it. Password equals XYZ. This is your MySQL password. If the web host assigns it, it will be listed near the host or user information. If you get to pick the password or change it, please don't use XYZ. Every hacker in the world has a program that will connect to your MySQL and try the 100 most common passwords. This is a placeholder. Don't use simple passwords like that. MySQL is a shared database. Lots of users are using the same database program, so everybody has to have a good password, so only they can access their database. Is seeing the password in the code a problem? Why, we're looking at a password right there. When hackers can open and read your Python code, security is already lost. Database equals test.db. This is your database name. There can be many databases on one MySQL server. It is tricky because some web hosts automatically assign a name, some add your account number to the name, and others let you pick any name you want for the database. While looking up your host or user information, check for it. Also important, web hosts have a simple utility to create/name your database. If you use that utility, you will set the name to the database created by the utility. Let's execute this code. SQLDB equals mysql.connector.connect. As the name implies, connect to the MySQL server. The variable SQLDB will connect to your program to the server, and then the server will do the actual read or write to the database files on disk. All access to the data happens through SQLDB. MySQL.connector.connect can be called with 3 parameters. Then an SQL command could be used to create the database. If SQLDB.isConnected, always check for errors. SQLDB.isConnected returns true when the connect worked and false when it does not. An error would be caused by an incorrect value for host or user or password or database name. Check your host documentation. If you don't supply the correct values from here, the connection will not work. I would have done more error checking on this slide, like after the execute command, if I had more room on this slide. It's extremely important to check for errors. Connected to MySQL host. A message to verify MySQL.connector worked. This only prints when it worked. When testing/debugging, you want to see this message, but on a live web page, not so much. Use a debug flag to turn it on and off. That's one way to go. Important commands like connect and execute, you should always check for errors after they execute. Print error no connect to MySQL host. This will only execute when connect fails. Number 1, the reason for the connect fail will be a problem with the 4 parameters. I wish I had room for more or better checks, but I don't. Should exit if there's a fatal error, terminate the program. Do not continue to the code below. If I could not connect to the database, there's no sense trying to issue a database command. Query string equals create table tab 1 ID int. SQL stands for Structured Query Language. MySQL and SQL are not the same thing. MySQL is a relational database manager that uses SQL commands. Oracle uses the same SQL. If, print, else, those are Python commands. Create table tab 1, that is an SQL command. To create a table named tab 1. This is the first of several SQL commands we will learn that work with any relational database manager. SQLDB.execute query string. Whoop. There it is. Execute sends an SQL command to an active connection, SQLDB, which then creates an empty table on the hard disk. The execution of this query created the table on the disk drive. All database changes assign an SQL command to query string and then execute. Bad. I did not have room to do another error check here, but I would have liked to seen an if-else statement after this. Misspelled words or illegal characters in the query string could cause this command to fail, and you certainly want to know if that command fails because without it working, you don't have a table. I'm running short of space on this slide, so I've got to kind of shorten the example a little bit. Like I said, I would have liked better error checking on this. And I want to say, at this point, since I've run out of room, I could show different options. There's no one way to program a database. There are several different examples. Some people build a cursor object first, and then use the cursor object to execute the query string. I'm sure I could code this 3 or 4 different ways. I just don't have the room to show you all 3 or 4 different ways. SQLDB.close. Very important. You must close the connection when you're done. Number 1, you don't get unlimited connections to the MySQL server. And number 2, the OS or operating system freeze locks placed on any disk files. SQLDB is not a simple variable. It is an object/structure that allows access and tracks the server connection. After a close, no more SQL commands should be executed on the database. You can see I've kind of disconnected the variable from the server. Do me a favor, Google XAMPP, XAMPP. This is an open source version of MySQL and a web server that will allow you to connect and use MySQL from your computer without having to upload anything to a server. It's a huge time saver. These are the default hostname, user, and passwords for XAMPP. The database can be set up to whatever you like using XAMPP's PHP admin. Basically, if you want to test MySQL on your computer without having to do any web hosting whatsoever, XAMPP is the program you want. ChatGPT wrote this program. I went on to ChatGPT and input the following question. Write a Python program to connect to a MySQL database. The host name is server.my.sql. The username is SQL user. The password is XYZ. And the database name is TestDB. And boom, it wrote it for me. It's that easy. ChatGPT is a revolution in writing database code. It's very, very good at writing SQL commands and small Python programs to allow you to access a database. As we continue, we'll use SQLite more than MySQL, but experiment with MySQL. It is the most widely used DBM for creating websites. If you're really into web programming, you need to play with MySQL. That's it for this video. I'll see you on the next one. Have a good day. Bye-bye.